Welcome, students, to the physics classroom. Today, I'm going to share with you the universal law of gravity, according to Sir Isaac Newton. If you remember, Sir Isaac Newton gave us the three laws of motion, the first law, second law, as well as the third law of motion. Sir Isaac Newton also gave us the universal law of gravity. To understand the universal law of gravity, or to understand the nature of gravity, we are going to go through this discussion, starting by looking at what happens when we have two masses, when we look at two masses, like mass 1 and mass 2. This is the center. This is the center here. According to Sir Isaac Newton, the two masses M1 and M2 attract each other. And according to his Newton's third law, this attractive force should be equal on each mass, independent of the size of each mass. So this force here and this force have equal magnitude and opposite direction. And this attractive force is called gravitational force. Now, Sir Isaac Newton told us that this force of gravity, number one, is attractive. In other words, it does not have to do with repulsion. It's attractive. In other words, the masses will be attracted to each other. Point number two, Sir Isaac Newton tells us that the force of gravity or gravitational force is directly proportional to the product of the two masses. So we can write that gravitational force is directly proportional to the product of the two masses. And also, according to Sir Isaac Newton, point number three, the gravitational force is inversely proportional to the square of the distance between the centers of masses. So gravitational force is inversely proportional to the square of the distance between the centers of masses. The centers of masses. It is very important to understand that the distance we are talking about here is the distance between the centers of masses. So let me use this red marker. So if I start from here, this is my distance we are talking about. This is the distance D there. Remember, it is the distance between the centers of masses, not from the surface, not from the surfaces of the masses, no, but from the centers. Now, Sir Isaac Newton's universal law of gravity can be represented as a mathematical equation as follows. So we use the formula Fg equal to G, you multiply M1 times M2, because the gravitational force depends on the product of the masses, and then divide by distance squared. These statements here can actually be represented by this formula right here. Now the value of G is actually, G is the gravitational constant. So G here is what we call gravitational constant. Gravitational constant. Some people call it universal gravitational constant. Gravitational constant. Okay, and its value, the value of G, is 6.67 times 10 to the power minus 11. It's a very, very small number. The units are Newton meter squared per kilogram squared. So this is the universal gravitational constant. And this is the formula or the equation that describes the statements I have shared with you here. So that's the nature of gravity. When you think about the Earth and interacting with the moon, we know that the two are actually attracting each other. Think about the rocket and the Earth attracting each other. You and the Earth right now attract each other. The sun and the Earth attract each other. And the nature of the gravitation, the nature or the magnitude of gravitation, the magnitude of the gravitation can be found using this formula right here. Now, it is very important to know that this number is very, very small. It is very, very small. So as a consequence, in order for you to notice gravitational effects, or in order to have appreciable amount of gravity, M1 and M2 must be large enough. If you have smaller masses, because of the value of G is too small, smaller masses do not produce substantial amount of gravitational pull that you can actually detect. For example, think about your cell phone and your cell phone maybe and the textbook. The cell phone and the textbook will not gravitate to each other because their masses are very, very small. You need huge masses of the like the size of the mass of the Earth, for example, or mass of the moon. Smaller masses will actually not produce a measurable effect of gravitational attraction. This has a very important lesson here. It's very small, and we have to understand that gravity, in order for you to appreciate gravity, we need to involve huge amount of masses. All right, that's the meaning of the smallness in G. All right, so to make sure we understand the formula and how it works, we are going to answer a few questions to apply the universal law of gravity, which describes the nature of gravity. All right, so we are going to start by looking at this question. What happens to gravitational force by the Earth on a rocket as the rocket gets further? So this is the question. What happens to gravitational force? I'm going to use just FG for shorthand. What happens to gravitational force by the Earth on a rocket as the rocket gets further, as the rocket gets further away from the Earth, so further away from the Earth. All right, so that's our first question. We want to see what happens to gravitational force by the Earth on the rocket. What happens to gravitational force by the Earth on the rocket as the rocket gets further away? Or what happens to gravitational force on the rocket as it gets away from the Earth? Let's make it like that. So what happens to gravitational force on the rocket as it gets away, further away from the Earth? So of course, you realize that we talked about that gravitational force is equal to G mass 1 times mass 2 divided by distance squared. And this implies that if the masses are the same, then gravitational force is inversely proportional to, we said, distance squared, or distance squared. So as you can see, if distance increases, then gravitational force will decrease. So according to this understanding that gravitational force is inversely proportional to the square of the distance, then the larger the d, the smaller the Fg. So we can say here that Fg decreases. So our response will be Fg decreases. So Fg decreases. Okay, that's what we can say right now. Now, we'd like to ask ourselves what happens if the distance is actually, let's start with doubled. What will happen to the gravitational force on the rocket? What happens to the gravitational force on the rocket? Okay, so the next part is what about if the distance goes to twice d? What will be the new gravitational force? New gravitational force will be how much? Well, we have to start by looking at the original gravitational force. The original Fg is equal to G m1 times m2 divided by d squared. Of course, here our m1 will be mass of the earth. Okay, our m1 will be mass of the earth. I'll put m subscript e. Our m2 will be mass of the rocket, m sub r, divided by distance squared. Remember, the distance is between the centers of masses of the objects involved. In this case, distance is from the center of the earth to the center of the rocket. So this is the original Fg. The new Fg, the new gravitational force, will be G is the same, the mass of the earth is the same, mass of rocket is the same, but now the distance goes to twice the distance, so twice d here, then you square that. Now when you do that, you end up with 1/4, then G m e, mass of the earth, mass of the rocket, you divide by distance squared. Now, if you look carefully, this quantity is actually the same as this quantity here, which we said is the original Fg. So what you are saying here is that the new gravitational force, new Fg, is equal to 1/4 of the original gravitational force. Okay, now to put this simply is that we see that now gravitational force is 1/4 of the original one. The gravitational force on the rocket is 1/4 of the original one. So that's the statement you can make. So the gravitational force on the rocket is now 1/4 of the original one. In other ways, the gravitational force has decreased, yes, but it has decreased by, it has gone to 1/4 of the original one. That's what we can say here. Now, what about if distance goes to 3D? So what about if the rocket has moved from the Earth and now we see the distance now it has gone to 3 times the original distance, so 3D. What will be the new gravitational force? So we are looking at new Fg. If you follow the same procedure, you can come up with the following. You'll find that the new Fg will be equal to G, mass of the Earth, mass of the rocket, and then divide by, this is now is the distance. The distance is 3D, so 3D squared. You end up with the 1/9. 1/9 of the original one, M E M R divided by distance squared. So again, if you look at this quantity, it's just the original gravitational force. So what we are saying is that the new gravitational force is equal to 1/9 of the original gravitational force. Original gravitational force. Okay, so that's the trend here. You can try. What about, maybe I may ask you, what about, try this one. What about if the distance now is 4D? In other words, if the distance increases like 4 times of the original distance, what will be the new gravitational force in relation to the original gravitational force? Again, try this. If distance goes to 4D, what will be the new gravitational force in relation to the original gravitational force? All right. Now, how about the mass? Maybe we should also ask ourselves, what about the mass? We have to ask if we, or before that, let's try to look at decreasing the distances. What about if the distance goes to 1/2 of the distance? Of course, you can tell here that distances has decreased, and you can guess that the gravity will be larger. When the masses are closer, gravitational force will be stronger. But by how much? To find that, we need to go through the same process. Start with the original gravitational force. So original gravitational force is written as G, mass of the Earth, and mass of the rocket. You divide by the distance squared. Now the new gravitational force will be, we are going to substitute D by 1/2D. G, mass of the Earth, mass of the rocket, you divide by 1/2D, everything squared. This gives you G, mass of the Earth, mass of the rocket, then you divide by distance squared over 4. Now this can be written as 4D ME MR divided by D squared. So it looks like when the distance is halved, in other words, it's half of the original value, then we have the new gravity will be equal to 4 times the original gravity. So the new gravitational force will be 4 times of the 4 times what? 4 times the original gravitational force, the original. Okay, like that. So gravity has indeed increased 4 times now. All right. Now, how about, let's try the mass. We are going to try to think about, you are on the surface of the Earth. This is a different question. It has to do with your mass. So if M1, one of the 2 masses we talked about in the universal law of gravitational formula, if M1 goes to 10 times M1, in other words, if the mass is increased 10 times, then the new gravity, I will just do this, the new gravitational force is equal to, so I'll put a dash here, original gravitational force. So what should be the blank space? Original gravitational force. So how best should we complete this statement? Well, we have to, we can think about it, but we have to show our reasoning here. So remember, original gravitational force, original gravitational force is G m1 m2 over d squared. Now we are taking m1 to 10 m1, so the new gravitational force will be G. Where there is m1, I'm going to put 10 m1 cross bracket m2 divided by d squared. So you can take 10 out here. This looks like just 10 times G m1 m2 over d squared. So this is actually the same as this, and this is actually the original gravitational force. So what you are saying is that the new gravitational force will be 10 times the original gravitational force, 10 times the original gravitational force. All right, you can go ahead and practice as many problems as possible to see how gravity changes when the parameters involved, the variables involved, when they are changed. All right, let's look at this question. This is our last question to discuss in this lesson. This question has to do with finding the mass of the Earth, mass of the Earth. You know, it is not an easy task to measure the mass of the Earth directly, and therefore we have to use physics to determine the mass of the Earth. Now, here is a problem. We know that we can easily measure the gravitational pull of an object near the Earth's surface. We can use Newton's second law to find the gravitational pull, force equal to mass times gravitational acceleration. Now, using that together with the universal law of gravity, we can determine the mass of the Earth. So here's the problem again. So Earth's surface. So near the Earth's surface, start like this. Near the Earth's surface, gravitational force on apple, gravitational force on a 1 kilogram apple is Fg equal to mg, remember, and this will be 1 kilogram times 9.8 meters per second squared. And the answer here is 9.8 newtons. Okay. I mean, I haven't used the universal law of gravity. I have just used the Newton's second law, force equal to mass times acceleration. And for gravitational force, we just use G, which is 9.8 meters per second squared. And I get my force on the apple as 9.8 newtons. Okay. Now, if the distance from the Earth's center to the apple is given, so if the distance from the Earth's center to the apple is given as 6.4 times 10 to the power 6 meters. Determine mass of the Earth. Okay, this problem involves us using both Newton's second law and Newton's universal law of gravitation. Already, we know that the universal law of gravitation tells us that Fg is G mass 1 times mass 2. So in this case, mass 1 will be mass of the Earth, and mass 2 will be mass of the apple, and divide by the distance. Remember, the distance has to be the distance between the centers of the objects. So if this is the Earth, the apple, so the distance is from here to there. So it's about the radius of the Earth. So this is about the radius of the Earth. That would be the distance that this is the apple. The apple is just like a dot because it's so small compared to the size of the Earth. So the distance is basically the radius of the Earth, which is given in the problem. Okay. Now we know the value of G, and we have also said that the gravitational force here has been measured using Newton's second law here as 9.8 newtons. So we can just substitute here 9.8 newtons will be equal to our gravitational constant 6.67 times 10 to the power minus 11. Sorry. And newtons meter squared per kilogram squared. Then multiply that by mass of the Earth, we don't know. Multiply that by mass of the apple, it's 1 kilogram. Then divide by the distance squared. So the distance is 6.4 times 10 to the power 6 meters. Then we square that. Now, if we solve for ME, this is the mass of the Earth here. If we solve for that, we should be able to find mass of the Earth as 6.0 times 10 to the power 24 kilograms. Okay, so this is actually very helpful. We are able to find the mass of the Earth using the universal law of gravity. Using this formula, in conjunction with this formula, we are able to find the mass of the Earth. All right. So we can also see here that our value for G is not always 9.8 meters per second squared. The value of G is only equal to 9.8 meters per second squared near the Earth's surface. If we go far away, the value of G decreases. Now let's see how the value of G behaves in general. How does G behave in general as we move away from the Earth's surface? Now recall that Newton's second law tells us that gravitational force on an object is mg. At the same time, this is the second law. Second law. At the same time, we know that gravitational force, according to the universal law of gravity, is actually mass 1 times mass 2. Let's think about the apple and the Earth situation. Mass of the Earth, then mass of the apple, m, just m, then divide by what? Divide by distance squared. Now, what Sir Isaac Newton is telling us is that the two expressions for gravitational force must be equal, must be the same. So this is according to universal law. Universal law. Now, the two must be the same. In other words, mg here must be equal to g mass of the Earth times mass of the apple, or mass of another object. This is mass of another object, mass of another object. If this is mass of an apple, this is also mass of the apple. Okay, so that over d squared. This must be equal. This must be true because the laws should not contradict each other. The second law and the universal law must not contradict each other. Now I can cancel out the mass here. I'll end up with G is equal to universal gravitational constant times mass of the Earth divided by distance squared. So what I'm saying here is that the value of G is 9.8 meters per second only near the Earth's surface. As we move further away, you see there's a distance here. As distance is becoming larger and larger than radius of the Earth, then we are going to see that this one will be decreasing. This one goes down, this one, if this one goes up, distance goes up, then G goes down. All right, so G is equal to 9.8 meters per second squared only near the Earth's surface. Only near the Earth's surface. Okay. Otherwise, we have to calculate it. We have to calculate the value of G using this equation here. And as you can see here, we might, if we know the height from the surface of the Earth, we can find our G as this. So gravitational constant, mass of the Earth. Our distance in general, distance will be the radius of the Earth, but we have to add the height above the Earth's surface. So this will be radius of the Earth plus the height above the Earth's surface, or the altitude, then is squared. So this will give us the new gravitational acceleration. This new gravitational acceleration works at that kind of altitude. But near the Earth's surface, where the radius of the Earth is the only distance there we can use, then we should be able to use 9.8 meters per second squared. All right, so I'll stop here. If you have any questions, please let me know. Bye for now.